This is Backporting Safety. My name is Taylor. I am an engineer at Bloomberg. I work on the Bloomberg Managed Services team in the queuing core group. Bloomberg Managed Services is like a service provider team within Bloomberg. So we work with a lot of like distributed systems and various other types of like generic services that you might want if you're an engineer building some code and you need some middleware or something like that. My team's particular is responsible for building, maintaining a technology called BlazingMQ, which is a distributed queue. It is something that I'm going to have to talk about for a little bit to get to the point of this talk. The title of the talk is Backporting Safety. This is a talk about safety, but I do need to give you all a little bit of an introduction to distributed systems first, if you're unfamiliar with these. So distributed systems, something like BlazingMQ, it has a lot of machines involved in the software that I write. Messages are constantly being passed and forth between processes, possibly on other machines, possibly through multiple hops. All of these machines or all of these processes need to be like highly available. It's very common for a network card to just sort of like fall over, or a machine to turn off for some reason, or something else is going on that machine that makes it impossible for us to kind of, the program that we're writing to do our job, right? So we need to be tolerant to a lot of these types of failures. We need to know about unusual states of the world that we really have no control over. And we need to be able to do this over a pretty wide network. Additionally, I can talk to you about this today because we did publish all of our code last summer. So all the code in the talk here today, you can go find on the internet. If you're curious to know more about how we designed this system, I encourage you to go check that out. But I do want to actually talk a little bit more visually here, since that was maybe a little abstract. This is sort of what a topology for BlazingMQ's deployment might look like. It's a graph, right? It's got nodes in it. They're interconnected. They might have certain relationships with each other. The green nodes in this diagram, they may be our clients that are trying to produce messages into our cluster. We need to be able to take those messages, deliver them to a node we call the primary here in blue. The primary is responsible for recording that information and then making sure it gets replicated to all the other nodes in the cluster. This process takes time. They're probably jumping across machines. They might be jumping across great distances. There's latency involved here. And then once that's done, once we're fully replicated, we can then deliver that message down to our consumers, right? This is a pub-sub type system here. And the system will go this way. What's one thing that's kind of unique about BlazingMQ is that this is a pretty simple deployment of this type of application, but we can go through more hops than just the direct message to the primary broker. Oftentimes, clients will have mini versions of the broker sitting on their machine that will act as a proxy in between the actual main cluster for helping distributing messages throughout their own deployments. So you can have an extra layer here in yellow here, these proxies we call them. In fact, you can have many layers of these proxies here. You'll notice that as we are adding more layers here, we kind of get an exponential spread of like possible machines that we're concerned about, processes that we might have to deal with. Some of these proxies may be running on the same machine. Some of them might be on different machines. All of our clients could be widely, distributed through the way that we deploy them. So yeah, we have a lot of different things going on at the same time. So let me tell you a bit about the requirements of BlazingMQ. BlazingMQ is a fairly recent technology in terms of like Bloomberg's total lifespan. It was started about 7 or 8 years ago, which is a while, enough to accrue a certain amount of like code, right? So it's a pretty big code base. And it was built on existing C++ libraries, right? That had existed even longer than before that, right? So we're kind of constrained by what those libraries can do, particularly networking libraries or base standard libraries. It needed to meet certain performance goals as well. Remember how I said all of those latencies between each of the different nodes and attempting to make the distributed queue work correctly meant that we're going to be paying for some amount of latency at some point. We don't want to accrue more. And we also need to be able to be like relatively reasonable to similar types of systems, right? We're not the first distributed message queue system. There's lots out there. And we needed to be able to be like comparable and ideally beat them in a lot of performance metrics. Another trick here is that we had clients that are running on platforms that do not have greater than C++11 compilers. They don't have C++11 compilers. They're working off of the C++03 standard support. We have other platforms which definitely are doing that, right? That are running off of the latest and greatest. They're on 17. They're almost about to be on 20. The path for 23 looks clear. So we can, get all the great benefits of modern standards on those platforms, except in the case where the language ties us to what kind of code we can express. So, yeah, we are kind of needing to support this older standard for those clients. Otherwise, the product's not useful. Additionally, like I said, keep in mind, because networks are networks, things happen. We may program our brokers to understand the world correctly and model everything right, and then stuff will happen, right? And the world will not look like what we thought it did, even if we kind of modeled everything correctly. So I said this is safety talk, so I'm going to get into the safety bits now, right? These are my concerns. I'm coming to you as a sort of non-expert. Lots of smarter people have said much greater things about safety. I'm going to quote them mostly now. But I do want to pull the room here a little bit. Like, when we talk about safety, like, what is it? What do we mean when we talk about safety?
Resilience to bugs.
Safety is about resilience to bugs. Okay. Security. Safety is about security. We saw those headlines from the security industry.
Robustness.
Robustness to what?
To unexpected states.
To unexpected states, okay. Yes, so the things that I said before. That neatly ties it together. Yeah, that's definitely one way that we could talk about it. Sometimes, though, when people talk about safety, they actually mean a couple of different things. They mean they're trying to talk about different types of safety that you can achieve. One of those things might be memory safety. That's what the security industry thing was all about, right? Like, they're very particularly concerned with memory safety issues. These are bugs, right, that prevent your code from being correct and doing the wrong thing. There's type safety, which is something that I think we're mostly pretty comfortable and familiar with. We like type safety in C++. That's why we have all these cool new types coming into the standard library. And there's also thread safety, right? Everyone here, I think, probably programs on a system that has multiple threads of execution. And if they don't have multiple threads, they may be working with like asynchronous executions. They still have to think about like concurrency as a concept here. So most people are working with these concepts, I think, already. These are the three types of safety that I want to talk to you about today. There are lots of other safeties that I've heard talked about, defined, particularly if you're working on a safety critical system. That is, if you're wrong in a safety critical system or you're engineering for a safety critical system, people die maybe, or lots of like real physical world damage happens. I don't think that's a risk for the type of software that I work on, and I don't have a expertise or a clear perspective on that. There's lots of other experts that do have that. Here, I'm just going to refer you to JF Bastian's talk from last year at this conference that kind of broke down these in more detail and particularly explored functional safety and things like that to apply to a safety critical industry. I'm not here to talk about that today, though. I just want to talk about these three. So what is safety? Again, what is it? What is it literally? What do we mean when we say that this code is safe or unsafe?
Some kind of provability or?
Provability. That's interesting. What do you mean by provability?
I want to prove that there are no memory leaks or stuff like that.
You want to prove that there's no memory leaks or other kind of like bugs like that. Okay.
It's predictable.
It's predictable. Oh, that's interesting. Okay, so predictable in what way?
In terms of you thought of beforehand in design, like your edge cases, corner cases, things like that.
Mm-hmm.
Refer to what will happen in those scenarios.
Okay, so like when you write safe code, or when code is safe, you can be sure that it's not going to do something you didn't expect it to do.
Or it will fail gracefully.
Or it will fail gracefully. Okay, that's some interesting ideas. There is a lot of, like I said, there's experts on this topic have already said a lot already. I'm just going to steal some definitions, but I like everything that was said already. They're very interesting, and they're all kind of branching factors of what we're talking about when we're trying to put our hands on this idea of safety, right? Sean Parent I think, had a really good definition for this from a couple of years back. The first, he defined what a safe operation was. He said an operation is safe if it cannot lead to undefined behavior. And then conversely, an unsafe operation may lead to defined behavior if its preconditions are violated, right? When we talk about unsafe code, we're often very concerned about the idea of what a precondition is for a thing. This is the talk that he gave, by the way, on this, where he said this. He might have been referencing other people as well. This was, like, I thought, a very succinct definition here about how to talk about safe code. So I'm going to make a simple argument about, like, why we should care about safety, and I hope it follows through, right? Why do I care about safety in particular? So the first thing is, we know that unsafe code can lead to undefined behavior. That's part of the definition of what unsafe code means. Undefined behavior, as already said, right, can lead to incorrect behavior, can lead to doing something weird that we didn't expect or not predictable. Some of that incorrect behavior is also quite dangerous. What you define as dangerous is entirely up to, like, your field, but in my case, it could be like, I work on a distributed system in networks. We're passing data across different machines. It could be very easily a security issue. What happens if that, some bit of data ends up in the file system, overwrites a buffer or something, and somebody else's data from one client, like Bank A's, proprietary information accidentally ends up in, like, a message destined for Bank B, right? That has, like, well, that's security. You can think about that as a security issue. You can think about that as a legal issue too, right? That's risk. So you got to think about what is an actual dangerous effect of the system that you're working on. The other problem here is, of course, that many operations in C++ just cause undefined behavior by default. They're in that group of unsafe code that have preconditions, and they're very easy to accidentally violate. There's been a lot of discussions about how to evolve C++ to make it a little bit easier to not have that be the default. Herb Sutter had also a lot to say about this type of thing, particularly about trying to make better defaults here. I think it's definitely, if you haven't read this blog post, it's definitely an interesting breakdown. My concern today here, though, is going back to where I am, right? I have to support a certain set of platforms, right? Evolving C++, improving it as a language in the standard is great, and I love to see it. However, I'm not able to write useful code I'm not able to make use of those revisions, right? The useful code exists in the C++ 03 standard to me because it's something that my clients can use, right? And if my clients can't use my product, then there's no product, right? So even though I can still play around with certain things, like, again, I am targeting future platforms that do have future compiler and standard supports. I'm somewhat limited in exactly, like, which features to the language I can access, or which features from the standards, the newer standards that I can access, particularly if it has to do with, like, language semantics, right? So my goal here today is we're just going to talk a bit about a couple of different ways safety bugs can appear. What are their causes? How do we stop them? How do we kind of, like, then design BlazingMQ in a way that tried to halt those bugs in a way that worked for us, right? I'm not trying to make any universal statements about how I like to fix C++ here today, right? I'm just talking about someone who works and maintains on a particular piece of technology with these particular requirements. What do I have the ability to do, and what works best for me? I want to then also talk about, take those best options and think about, like, what's coming in future standards that we can then pull back into in like a backporting sense, right? Literally, we are taking these ideas and being able to re-implement them at some level, right? In the older standards, right? So we're going to start with memory safety. What is memory safety? What does it mean when your program is memory safe? Kind of a hard question, right? Like, I think we all have an intuitive understanding of what that means, but there's like a very specific set of things that I'm looking for.
No risk of access violations.
Access violations. Okay. Access violations to what?
Like out of bounds, just in general.
Ooh, out of bounds, right. Yeah. No reading, writing out of bounds, right? Yes?
Respecting the lifetime of objects.
Respecting the lifetime of objects, use after free, right? You've got some bit of data, it deletes, you still have a pointer or reference to it, dies. Anything else? Yeah?
Type safety, like not accessing an object as if it were another object that it's not.
We'll get to type safety in a second. That's a separate safety like category here. But yes, type safety is important for, we'll get to that in the next section.
Race conditions.
That's the thread safety section. Different type of safety, right? We're just talking about memory safety bugs. How do you define
memory?
Uninitialized, yeah. Right. Oftentimes I hear these things broken into two categories: spatial memory safety bugs and temporal memory safety bugs. Right. One having to do with like literally like what range of values you're allowed to write at, and then the other one having to do some property with the lifetime of the data that or the type that you're working with. There's a paper that kind of explores this very deeply here. Go check that out if you like reading papers. This is like a very, very dumb summary of it. So undefined behaviors, that's the thing that we have to, that's the thing that's making our code unsafe, right? An unsafe function, preconditions are not met, we get undefined behaviors. Those undefined behaviors might lead to these types of memory safety bugs. But they're all over the standard, right? They're just an inherent part of how we do C++. They always have been. They doesn't seem like we're stopping that. Like future, the most recent standards haven't like stopped introducing interfaces that are completely safe or something like that. It doesn't seem like that's like the direction C++ is taking, nor does it really. It has good reasons not to either. So we'll never really have a complete solution from again my perspective. Maybe someday in the future we will. We'll have a nice complete solution. But today, right, I have to deal with this. So can we embrace undefined behavior in the way that like I think this like we kind of are expected to be able to use undefined behavior in a productive way? Let's go down each of those different cases that I have and think about how we can like patch up some of our undefined behaviors where they exist. Starting with out of bounds indexing. This one, I think this one's often considered the easiest one. Here's some like toy example that I came up with, right? This is a class. It's got some function that it's got some member function. It takes in a size t and indexes into an array. The problem here, of course, is right here, right? That's unsafe. That's an unsafe operation. There's no bounds checking done on indexing into an array or a vector, right? I guess I didn't explicitly declare that was a vector, but like it's a vector. Let's just pretend. If it's not, if this is out of bounds, right? We're in trouble. So how do we fix this?
Use something that has bounds checking.
At.
Use something that has bounds checking. Okay, we could make the function safe.
Dot at.
Dot at, right? Throws an exception, right? Dot at is an example, right, of a version of this operation that is safe. It's completely defined, everything that you could do with that. If you're out of bounds, you throw an exception, right? That's a safe function. Okay, sure, that's fine, but there's costs to throwing exceptions. In particular, in my system, I can't use exceptions. It's just not a thing I can access, right? So, not an option for me. What else could I do? Die. How?
Abort.
Abort. How do I abort here?
If size ID not in the
Okay, yeah. If do the bounds checking and
Yeah.
then like
Abort.
std terminate, right? Or abort or whatever, right? Sure, yeah. Actually, there's actually something even simpler that I could do here, right? I could write a little doc string that says like, hey, by the way, you need to like do this in order for this to be valid, right? Yeah, I'm defining the precondition here. This is an unsafe function, right? It's got preconditions. So I can just tell the user, first of all, what it is. And then just let them like pay for it if they have to deal with it. It's a choice. What I find with this choice is that I, the author of this code, end up also being the caller of this code very frequently. And I also very frequently don't read my own documentation. And I end up bombing out somewhere. So we can go even further with the abort idea and actually do try to check it, right? But here, I'm using a macro that I'm just going to call contract assert. And if anyone's read the contracts paper, That's a choice that I've made on purpose, where I have this like ability to not only actually do the bounds check, right, but also I can decide whether or not I want this bounds check to run because it's hidden behind a macro, right? And at compile time, I can be like, turn on, turn off, or do something else, right? Maybe abort is the right choice for a lot of cases for me. Like I really, really, really don't want this to be out of bounds, but maybe I like, abort's not the only option here. This is a macro. I can insert whatever code I want. I can be like, all right, like I'm going to call some hook or something that decides whether or not this is a real problem or not. So this is like what we would call a contract, right? This is contract programming. I chose the name of the macro because it's the same keyword that, except in lowercase, that the contracts paper that's in progress for 26 uses. Contract programming, of course, just as a brief review, you will take a set of preconditions on a function, or potentially a function has postconditions that would run after the return actually happens, or just like assertions that can happen anywhere in the middle, right? Through that contract assert call. And what it does, the idea here is that we're not necessarily forcing our functions to be completely safe. We are taking an unsafe function. We're not necessarily changing its behavior so that it's well-defined on all inputs. But in fact, we continue to preserve the old behavior, right, for types that already existed and things like that, existing code, legacy code, and give us an ability to like step in the middle of the function when undefined behavior is about to happen, right? Because the undefined behavior that we're worried about, things like vector and array indexing and out of bounds, that's something that the compiler makes a decision about, right? I don't control the compiler for the most part, right? There's maybe a few things that I can do with like sanitizer and stuff, and we will talk about a little bit about sanitizers, but like for the most part, I don't control that process. But I don't want the undefined behavior thing to happen. I want to choose what that undefined behavior is for me. So I'm kind of fronting a lot of this unsafe code that already exists with my own unsafe code where I have some ability to rig what happens when I fall out of contract, right? And if you notice from before in that doc string, I said explicitly in the doc string, the behavior is undefined if you're not meeting this precondition. There's other choices you could have made there. You could have said the behavior is unspecified or whatever, right? Like maybe there's some other way that you could do it, but I'm specifically invoking undefined behavior on my own function. So for us, it's contract programming that makes a lot of sense to solve this bounds checking problem. I mean, bounds checking for arrays is like, that's the choice that you make. Every interface that you have that can like index into an array or something like that, where a bounds check might happen. Instead, we can kind of front it with this contract check, and we have a system now that we can use to like catch with these contract violations. And if we need to take them away for performance reasons for like certain production cases, we have that choice. We may not make that choice, but we have that choice. We won't know until we measure our code, right? It's a question about performance and safety, but we can't know things about performance unless we measure them, and we can't measure our code until we've fully written it. So this is a decision that we have to make pretty early on to allow us to control for something that we won't know until much later. Let's talk about use after free. It's like stepping from P into NP hard, right? Here's your classic use after free scenario, right? Let's say we have this event queue type. Calls get event, returns an internal reference to some underlying buffer, right? Collection. Who knows? Doesn't matter, right? We're returning a const ref out of here. The question is, like, what do we do, right? About like what do we know about that returned event reference's lifetime? Is it bound to the object that we got it from? Is it maybe bound to something else? Is maybe that object holding on to a pointer to another thing? We don't know necessarily. So like, could we validate somehow whether or not that event is alive before using it in some way? Not really. There's no like magical is alive function or anything like that. In that case, is there some responsibility that the event queue could have to its callers to ensure that the references it returns remain alive? What are the choices here?
Depends on what's an event. You could copy
True.
the event instead of
Same.
Right. We could just make it value semantics and
Yeah.
just like be done with it. Right. Maybe that's the better choice is just like don't introduce the lifetime at all. Right.
Yeah.
Maybe that makes sense. Maybe copy's fine. Maybe copy's not fine.
Yeah. It's hard to know.
Let's say the copy's not fine. Right. Because we do have points in our code, right, where that's not a reasonable choice. But it would solve the problem, right? So that is like, I think it's a valid solution here. But it wouldn't apply necessarily universally.
So what you can do, you can make the popq function take a reference to the event and then check that it's the one that you gave out.
You can,
And therefore verify that the user, like, I mean, you take an R value reference to it, and it's like, okay, that gives the user a syntactic marker that that's done, and it's going to go out of scope. Like it's a
I see.
batch. Like that's what we do a lot with like locks. Like if you're not the one locking, but you need it to be locked, you get a lock guard as your input, right? To make sure that it's actually holding the correct mutex, and therefore you don't have to use recursive mutaces and stuff.
So the goal here, I think maybe if the interpretation for this example, right, is to lend out a type that ensures that that event stays alive or can be validated
No,
through.
it's more like you can't even pop the queue without moving the event back into it. It's like,
Oh, I see. Okay, so like move it out of the queue and then hold a lock on it.
you can literally give it. You can give the user a nil value reference, right?
Mhm.
And they're allowed to move from it. They're allowed to move from it twice. Like that's fine.
Mhm. From a
point
const style
is-
value reference?
Sorry?
From a const style value reference?
No, not a const one.
Okay.
But I mean, you could also give them a const value reference. The point is, you want a std move marker on popq.
Mhm.
Like, oh yes, I'm still holding on to this, and yes, the one that I'm popping is this one, and I swear that I'm not going to touch it again because I know it's going out of scope. Like, basically, you give the user some token that they need to give you back once they're done with it, just so that you get a syntactic marker on the call side.
Okay, so it would be a cooperative. It would be cooperative from the client has to communicate back to the event queue that, hey, I'm done using this
I
thing.
mean, they have to do that anyway, right? Because they call popq. It's just whether popq requires you to prove that you're done with it.
In this re-implementation, you're popping off the queue and
When you're invalidating the events front, right?
right.
That's when you need the person you gave the event to.
Mhm.
You need them to prove that, you need to make them have a syntactic marker that's going to show the programmer reading that code that this object is done and they better not access it again. Like that's the best we can do.
Okay.
It's not great. But
But
a
it-
syntactic marker is better than no syntactic marker. Like
Okay.
It has saved people who, didn't know what they were doing.
Sure. So syntactic, a way of basically making it part of the syntax, sort
Yeah,
of.
like you can't call popq without saying this one, and I'm not going to see it.
Right. So right, I could write a contract here that says like, here's the lifetime of the thing I'm returning, or I could make a syntax, make it part of the syntax in the way that it's called to be more explicit about how you're supposed to take the lend of this.
Yeah, like if you
out.
look at Lisa's formulation of this, right? This queue is giving you a responsibility. Like you're getting a capability,
Mhm.
right? That you can access this event,
Mhm.
and until you give that capability back, there's nothing that gets to invalidate front.
Okay. So there's no other function on event queue that could possibly invalidate the
Well,
underlying.
no, they all just need to receive your like I'm done with it back, right?
Okay.
Like this
I'm
could
gonna
be
have
like
to-
some weird algebra. but-
Yeah, I'm gonna have to check out more of that idea because that's a new idea to me. Yeah.
The one other simple solution would be to share pointers.
Yeah. That's a really dumb solution, but it works, right? Like
Yeah.
this is like the guaranteed way, right? Like, I mean, how do we feel about this though?
You can now make
Sometimes you don't have
I'm now
way
doing
out
what?
of that.
now your entire program is one data structure.
Yeah. It's not great. It's a form of garbage collection in a lot of ways. It's obviously the wrong default for many applications. I can prove that because we had a garbage collector in the standard at one point, and then we removed it. I think that was like a tracing garbage collector, right? Was that more, or was that more complicated than just like a bunch of rep counting? No? Okay. It never worked. Well, obviously the wrong default, right? You have to admit it does solve the problems. It solves a problem, doesn't necessarily prevent other problems from popping up. But for some, it is the right default. And you do have to admit shared pointer is like a form of garbage collection, and it is useful in certain contexts, right? It's parts of your program, not the entire thing, right? It's definitely not right for us, right? Shared pointer is right for us, but like a full tracing garbage collector or things like that, not the right choice. Okay, so like garbage collection is like maybe an option here, but like maybe probably not. What are our other choices here? We've already talked about a few things related to this. I'm going to talk a bit about allocators before we move on to this point, because allocators are obviously the wrong default, custom allocators. Obviously the wrong default for a lot of applications. They do solve the problem that they're trying to solve though, right? Control over your memory allocation. And for some, it is the right default. And for BlazingMQ's case, it's right? We have a fully like custom, deeply embedded allocator aware system. Why? Why do we do this, right? Because we're trying to test for leak detection, right? We have a set of test cases, right, where we have a ton of brokers running on a ton of different machines. A lot of them we don't own, right? Like they're not ours necessarily, they're client machines. They may be client as in like other engineers developing applications that we're also running on their machines, right? So we kind of have to share the machine resources with everyone else. And we may also be running for very long periods of time, these brokers, right? And we're passing lots of data through them, right? Millions and millions and millions of messages. If we have memory leaks, we can very easily thrash machines for ourselves, which would be bad. We could thrash machines for other applications that are running on that machine, which would be really bad. So we don't want to do this, right? We thought ahead. We were like, we need to be really clear on memory leak detection. So one of the things that we can do in our tests is not only do we kind of have our own custom allocator that will, track allocations, but it will throw contract failures when we clean up that allocator at the end of the test and decide and look at like what is still allocated and go, oh, there's still something allocated here, right? And then we can use our contract system to check that. And in tests, contracts may do something different than they would do in production as well, right? So we can control a little bit of that behavior for whatever makes sense for our test case. And if we were to actually use this in a real system, we would be able to do even more interesting things. It's like having a little mini Valgrind, right? Not the full Valgrind attachment or anything, just a little tiny feature inside there. This is a very useful thing. Right? Lets us catch sort of naturally this thing that would otherwise require, I don't know, it'd be much more difficult for us to keep track of, well, it's not necessarily more difficult, but Valgrind comes with certain trade-offs, or Valgrind, which one is it? Valgrind comes with certain trade-offs. This one, very lightweight solution for us within our test framework, and it lets us use it everywhere. So I'm going to kind of enter into a sort of a magical speculation world. Kind of bear with me here for a second, because that's the extent at which we use allocators within it, right? We can catch memory leaks. Memory leaks aren't necessarily a memory safety problem. They are related to storage, duration, and everything like that. But they don't really necessarily have anything to do with this like use after free thing. But there is a couple of blog posts from the Chrome team where they describe a technique that they are using within Chrome called Miracle Pointer, where this is a smart pointer type that they have implemented that works in conjunction with their allocator that they use specifically for Chrome. It's a global allocator. I don't think they're necessarily using customized allocators or anything like that. The key here, though, is that they're trying to catch these types of use after free bugs. And the way that it works is that the smart pointer is coordinating with the allocator to keep reference counts of known usage of raw pointers. They have this special type. It's called raw pointer, and they can wrap the existing uses of raw pointer, and there's an equivalent for references as well, to keep track of like where in the program is using things. And when a free is called on the actual type, right, when you're actually trying to destroy it, it doesn't release the storage, thereby ending the lifetime and opening you up to all these use after free bugs, and instead quarantines that memory somewhere else. And it keeps track of that reference count that it was using when it allocated the storage for that type originally. When that reference count hits 0, then it actually frees the storage, right? But before it does that, it poisons the memory that it's being used, right? Overwrites it with a bunch of like random values, right? In the hopes that if there's some like existing pointers into that block of storage, right, that when it tries to read it after the lifetime, it's going to do something dramatic and like crash in like a hopefully predictable way. It might not, because the storage has been freed. It might be reallocated later on. But it's a sort of an optimistic way of trying to balance a bunch of these trade-offs. They have a bunch of interesting like write-ups that are like mostly publicly available for people to look at how they kind of compare different algorithms for choosing this miracle pointer implementation. It's very interesting work here. But yeah, we talked about this, right? And this is how they keep track of the reference count. This is mostly managed through the raw pointer, right? So this gave me kind of an interesting idea, right? Like we have an allocator coordinating with smart pointers. We could very well decide to choose something different for how this raw pointer type works for ourselves, right? And we like contracts. We have this whole contract system that exists, right? Instead of like managing a ref count, we could also manage a ref count in the destructor and constructors here, whatever algorithm we choose. We could also choose to inject this like contract here. One of the nice things about the Chrome implementation of Miracle Pointer is that that operator is just one line. It's just the return pointer. It doesn't do anything other than what you would expect the pointer to do. We might want that to happen, right? And then maybe we could check something about the aliveness of the data that we're looking at in conjunction with the allocator that we are using. That would be kind of nice. And in fact, if we could go through and find all the different references that we have in the code and do a similar type of process, we could maybe expand the level of awareness we have of the liveness of a pointer or the data that we are trying to reference. It doesn't fix everything though, because of course this only really works through raw pointer specifically if there's some existing reference type or some pointer that we haven't like converted yet in the code base. We're still sort of open up to these problems. We cannot like generically override operator star on like types, like int pointer, for instance, for us to like inject in our own contract assert, customized contract assert code, right? The best thing I could really think of doing is like, we have this function that like does nothing and just sort of asserts that, you know, this pointer or this reference is actually alive in conjunction with whatever allocator tricks we are using. And then like all code ends up looking something like this, where like anytime you actually use it, you have to like be like, I'm asserting that it's alive, right? And then you actually use it, and then maybe the contract assert goes off. This kind of sucks though, right? Like I don't even think it necessarily solves the problem here, right? Because again, like if this was the code that I was writing, why wouldn't I just change that to raw pointer, right? If I have to make a code change in order for this to be correct, right? I can't get, like what I want to be able to do is get into what the compiler can do, right? And define what that like basic pointer indexing operation does. It also doesn't help for things like I'm passing things off to like other libraries and stuff that maybe just be using this, and I don't have any control over what that library is doing with pointers and types that I pass to it. So what we do know is that dereferencing invalid pointers is undefined behavior, right? Clearly. That means that the implementations get to choose what that that does. They could choose to make that a contract failure. They don't, for a lot of reasons, particularly because contracts are still a paper. But there's also like performance and efficiency reasons to think of. I'm not a compiler engineer. I don't know necessarily what all the trade-offs here are, but I could imagine a few, right? But let's say, like, what if they could, right? Would that be a better default for us? Right? It does require some amount of coordination with an allocator, possibly. It may be a bit heavier than like what you could get by like what we get today. Maybe that wouldn't be a great option for everyone, maybe this would be more of an opt-in than a default. If it's a contract, then maybe we just compile it out in most cases, and it's zero cost. And then, like for me, I could turn it on if I want it in certain places. I don't know. I need to be able to like get into the compiler in order to do this. That's the end of my speculation here.
Memory sanitizer does that.
Yes. So that's a great point. And all the sanitizers, msan, asan, they're all working with the compiler to inject extra behaviors in here. Yes?
Do you want feedback on this speculation, or do you want to keep going?
How long would that feedback be? Because I do want feedback.
Okay, I think that from the compiler's perspective, right, turning this into a contract failure, it requires the high cost thing. Like we don't have, like it's not possible. Like the thing you're searching for is a way to detect this cheaply without running a garbage collector. That's also what the compiler would need, and it doesn't have one. Right, like the sanitizers use shadow memory and
right.
in order to implement this, but at great cost.
Right.
That's the cheapest technique we found.
What I believe that, right, because it hasn't been done already, right? I feel like I have more questions, but I don't want to. I want to get through the presentation on that. I definitely am throwing this out as like crackpot speculation about like what if we could just turn off the trade-offs here. But of course, wouldn't that be nice? In a lot of ways. So let's talk about uninitialized memory. For us, like the only thing we really have is like constructors, right? It's constructors aren't really the answer here. There's a lot of types that don't have constructors, like the primitive types and things like that. All we can really do is be really good, right? This is sort of a guideline thing more than anything else. Be really good about when we have a constructor or when we're using an object, we initialize everything to some known value. So it's right for us, like a lot of people, the right default is like uninitialized values for these types of for like primitive types. And for us, we just want the default to be like it's initialized, right? There's no option for us to do this. We just kind of have to like be really good about it. I kind of actually really struggled with this for a while trying to build up this part of the presentation until literally yesterday I discovered this paper that is moving through the draft right now to try to define a new set of semantics that seems to exist between well-defined behavior and undefined behavior called erroneous behavior.
This is in the draft.
This is in the draft, yeah?
It passed core.
It passed core, okay. So this is kind of an interesting idea to me. And I'm kind of glad I found it just yesterday, although that means I haven't had a lot of time to think about like what it could mean. But why is it here? It's specifically trying to at least target uninitialized reads and give a new semantic to what reading uninitialized data would mean so that it's not like wildly undefined behavior, but maybe something else. It's interesting. They have this like matrix in this paper here about all the different possible applications they might be thinking about, what they might want to try to define as erroneous behavior, and what they think is worth it, what they think is not worth it. It's an interesting read, but I do want to highlight at the end, there was like a speculative bit here about using contract violations as a way to implement whatever erroneous behavior means, as far as I understand.
So
maybe me misreading it.
There's another paper in flight. It's P3100.
Mm-hmm.
It's going to be in the next mailing. It's going to try to just make uninitialized reads instead of erroneous behavior a violation of the implicit contract, and then this basically allows the compiler to do whatever this paper already does.
Okay.
Just harmonize contracts with erroneous behavior and basically say if you're violating a precondition, even if you didn't check that, that's erroneous behavior.
Okay.
Right.
Cool. I look forward to reading that. Yeah.
I think there are kind of two things that are maybe worth separating when you think about this, though. You're talking about like contract violations, and I think that's a good way to maybe think about what happens once you've discovered you're reading uninitialized memory in some way.
Mm-hmm.
But it doesn't really speak to how you discover that a particular read reads uninitialized memory.
Mm-hmm.
And there's kind of a separate set of questions there that contracts don't help with, that I think are actually the other thing that is really tricky in this space. Like this is going to let us limit the blast radius of uninitialized reads, but it's not going to get you to the point where they're safe.
Right.
Because you really like, and one of the big limitations is because we don't have kind of reliable ways of detecting whether a read is uninitialized, and should then have contract violation or whatever other behavior you want.
Yeah, that's a really good point. Like, and this is, the idea that like this problem is still generally hard to solve. Like, this is a possible solution when you figure it out, but how to figure it out is still like basically intractable. From maybe not, but it's really hard. And and I also don't think that when we're using contracts in our code base, we're not necessarily saying this function is now safe to call as well. We are saying this function is still unsafe to call, but we are rigging it up with the instrumentation that we want. That instrumentation may in fact be much lighter than a sanitizer's instrumentation. It's not complete though, right? We're still going to always have to deal with the existence of undefined behavior, kind of leave it lurking everywhere until we get like proper safe interfaces for everything. Just to give you a tour a little bit of what that code looks like. I'm spelling contract assert as BSLS assert safe. This is the name of the library that we are using. We've had this library for a while. This code, like if you're curious to know, this is from the BDE project. It's also open source. You can take a look at it if you're curious what that looks like. This is just how we spell contract assert in our code base. These are what like our precondition clauses end up looking like. In the contracts paper, all those preconditions would actually be like above the function block here, and they'd be in a little thing called pre, and you'd have a bunch of list of them, and it's great. It's like syntax for this thing. Right now, we just kind of have to do it the old-fashioned way. Leave a comment. But you can see here, right? We're doing things like, okay, we need to check that our URI is valid. We need to check that we're in some thread that makes sense, right? We need to do a range check on this partition ID integer here, right? We need to do null pointer check, right? Like that's one thing that's pretty easy to do with contracts is like, I'm not even gonna know. Yeah, these are all parts of the contract. If you were to like scroll up to the docs, you would see it. Post conditions, we again, what I think is we kind of have to do the old fashioned thing of being like, let's put it at the very end of the function before we return. In the contracts paper, the post condition will run literally always after the return happens. I believe Boost also has a contracts library that uses like scope rules and a lambda to like make sure that it runs when the destructor of that type gets called. We don't have lambdas, so we just have this, but it's fine. It's okay. It can be error prone. We have to keep up guidelines to make sure that it continues to work the way we expect it to. But we can do things like check to make sure that we didn't get a weird number back from the function. We're not returning something that is like unusual. We can also do it right middle of the function. There's no reason why we couldn't call it. It's just macro, right? In this case, I think this example is interesting because the contract is not dependent really on user input here. This is a little bit hard to see if you can't read the code, but this expression here, 0 is less than padded len, is dependent upon this Q record header type at the top of this snippet here, which is not a user input thing, right? That is just some function that we are calling in the some other part of the class, right? This is like some contract check that we are doing that has nothing to do with preconditions, right? This is another application for contracts here. Although you can maybe say like, if that's a method on the class, then like maybe the class has to be in some state, and then the precondition can be like the state of the class needs to be this, and maybe that could itself be a different contract check, things like that. Okay. That's all I really have to say about memory safety. It's a hard problem. We do our best, but these are the solutions that we have, and we got a couple of interesting ones I didn't think of. Type safety. Moving on. Type safety is about trying to, as somebody already said, right, like trying to prevent invalid operations on data that already exists, right? We have types so that we don't have like, we can't add a string and an int together. Like that doesn't make sense. We like that. It's good. We are doing this a lot already. There's a lot of types, right? Where the sort of intuitive solution, the intuitive definition here is like we're trying to make it hard or impossible to do the wrong thing with the data that we're working with. Some examples, of course, might be like optional and invariant. We have like our own type for URIs, representing URIs. That's how you connect to different endpoints within a cluster. URIs, we could just have made strings, but URIs are like very specific things. They have a very specific format. We want them to maintain that format, and we don't want to accept just random strings. We will want to be able to convert from a string to a URI, but then once we're there, we want to be like very confident that we're not working with something that doesn't make sense and that we won't be able to look up the domain of or something. Additionally, we have like a schema that you need in order to talk to the BlazingMQ brokers. All of that schema is defined well within a series of message protocols. There's a series of types that go with it. They're all composed together. They're all serializable. They're all deserializable because they need to go over the wire. Right? These are the types of operations we want to be able to have on our data here. And it prevents bugs. I really don't know what else to say here. I think most people are already on board with type safety. Is anyone not on board with type safety? Yeah.
One thing that crossed my mind when you talk about uninitialized memory is using strong types
Yeah.
for your floats and doubles or whatever.
Yeah. There's a way to, we could,
initialize them.
yeah. What you're saying is like, there's a way to, what we could do is say like ban ints, floats, doubles from the code base. And instead we're going to define our own type called BlazingMQ. Or even, something like that, like a constrained type.
Yeah.
Like that partition ID that we were using, we could have, that was an integer in that previous example before. Mm-hmm. We could have said partition ID type, right? We could have had a type name for that. And constrain that upon whatever matters, right? In this case, it was just an index. So, but that the fact that it was an int underneath, or that it was an index, was sort of leaking through the fact that we use an int as opposed to like our own custom type here. More tools to do this. I think in general, like this is a thing that other people are doing, right? I don't think that's a novel idea. It's kind of hard to do, I think, because it's kind of hard to like define classes for all of these things. There are certain types where it's definitely worth it, like that URI example, right? I think if it was just easier to kind of do this type of thing in a way that like I could access with my C++03 language utilities, it would probably be an easier thing to just build more code for, right? And be sure that it's working. Any other thoughts? No? Okay. So one of the nice things about type safety is that I feel like a lot of the point of having things that are type safe was to try to prevent some of the safety bugs in other safety categories, right? Memory safety bugs in particular, right? A lot of the types from the future standards are literally backportable. I mentioned already shared pointer. Shared pointer was not in C++03. That's not something that I can just use as part of the standard library, but it's an extremely backportable type, and it's extremely useful. Unique pointer, not so much, although you can kind of fake it. Optional std is definitely one of those things. Unordered map is, just, a lot of like reasons the standard libraries was enhanced in future standards were like, we have this thing, it already exists. Why don't we have it in the library? It would be useful. There was nothing language specific about it, right? Preventing us from reusing it. Array as well. Nothing particular about array that prevents us from backporting it back into C++03. Some of these types you might even think of something like variant, for instance, right, is reliant upon variadic templates, which I don't have access to. But again, you can sort of fake some of these types. There are some operations that I don't have access to, but I can sort of fake a variadic template if I use all the different if I go from like 1 to 10 or whatever, and I usually don't need more than 10 variants, or really honestly don't need more than 5. So like you can get around these things. There are ways to deal with it. They may not be exactly equivalent to the standard, but close enough, right? Another example is spans, right? Like spans, they're not like a wild concept or anything. They're just like, we have a pointer and a range, or 2 pointers, and we just say like, this is a view into the data here. We can also throw contracts on this stuff when on construction, so we can be sure that like the span is well-formed, or at least well-formed enough, right? Interestingly here, this doesn't encapsulate everything that we might want to know about a span, particularly whether or not that span is overreaching into outside the bounds of some like valid memory here, right?
And it is a reference. It is a view, a reference to something else that might be.
We could still misuse array span here, right? Especially if the underlying data goes wildly out of scope, right? But even still, right? Because like the useful utility here is like we can take something like, right? This is what I was talking about earlier. You can take something like the indexing operator and put your contract checks in here. For us, this is really valuable, right? Because we have this instrumentation set up everywhere. We can redefine what these operators do at a certain level, right? If we just used span as it was, we might still even have a reason to try to like implement our own layer on top of it, just so we have contract compatibility. It'd be really useful if like some of these things existed in the standard library in future standards once we're able to access those on the platforms that we can compile for the later standards. I don't think I have any more to say about type safety there. Like I said, I think most people are on board with why that's good. Does anyone have any other questions about that? Okay. Thread safety. This one's tricky. In order to understand thread safety, we have to talk about data races. What's a data race?
An unsequenced read and write where that matters.
Right. When you have two threads that are using some data at the same time, at least one of them is modifying that data, right? It is undefined behavior by the standard in C++ 11 and above. C++ 03 does not have a notion of threads as far as I understand, and thus we still treat it as undefined, but I don't think it's actually technically there.
Well, it doesn't talk about it. It's undefined.
Okay. I guess yes. By definition, it's undefined. There's literally no text for it. Yeah, right. This is bad, right? It can cause objects to become invalidated. It's almost certainly doing the wrong thing again. That probably, again, leads to the incorrect behavior or the dangerous behavior. Even further than that, it might trigger other kinds of safety bugs that can appear. You can actually end up causing other, like, you can get up in a weird state, change the size of like the buffer that you're writing to, and end up like accessing, like ending up with like a much bigger capacity than you actually have allocated or something like that. It's a problem that can lead to more problems. How would you fix a data race? Well, you can make everything const. This is like the functional programming solution here, right? Is everything is immutable. You remove one of the qualifiers of that definition from before. There's no writers, so you can't run into a data race. It works. It's not the right choice for us, but that's like, I think there's a whole space of immutable data structures that is out there, and that like that's one of the benefits is that you can be highly concurrent and continue to make copies of things and know that they won't change as you're doing your running your algorithms on them. Some other ways, there's the classic, you got to sync access to your readers and writers over mutex and atomics and things like that. This comes with its own batch of problems. You can, for instance, deadlock in this setup here. That doesn't create a thread safety bug in itself, but it does create a problem in the system. There's ways to write good code that prevents that from happening. It's what we do in our code base. Like, we're not using this method here. It is a good default for a lot of people, right? There's also a third option here, which is to go back to that other definition of two threads. One is writing, at least one of them is writing, which is to just make sure that none of the threads are able to share that data here, right? If there's two threads, but neither shall the two meet in terms of the data that they're working with, then you avoid that problem. This is one solution that we choose as well. We choose both of these things. We have some parts of our code base that are using mutexes, but we do have a significant part of our design that is based upon not sharing data. And how do we do that? We use the actor model design pattern, right? For those of you who have not heard that before, it's great. the actor model means you're not sharing memory between the different processes that exist within this design. How do you define what a process is or what an actor is? It's a little bit more abstract. In our case, we're just using some basic threads. We only have a few actors going on in this system. The idea here, though, is that each of these threads that represents this actor are sequencing their own operations, and all the data that they have in there is not communicated with other actors in the system, or not shared between other actors in the system. The one thing they can do is pass messages to each other. That's copied value semantic type data, right? They better not be passing references around through the little channels that they have to talk to each other, because otherwise then we run into our problem again. That message buffer, by the way, that the way that they talk to each other, that thing has to be thread safe. That is shared between two ends here. There's ways to design around that, but that's the only piece of the system that needs to be like thread safe and correct. So how do we use it? To just break it down a little bit, we have one actor that kind of talks with our clients, the sort of incoming requests that are sitting in the broker. This piece exists within our broker. They're responsible purely for reading and writing to a client. They also keep track of stats and do message validation, right? Their responsibility is very isolated. It's another key thing to making this work. We don't have like one God object that is like the actor. Otherwise, everything's happening in one thread and not good, right? That actor, once it's able to communicate with the client, gets a message, maybe decides it needs to forward it along somewhere, it needs to go to the next piece of the system, which is the queue actor. That queue then is responsible for just doing like storage and replication and managing the file system and things like that, routing data, figuring out which cluster, which node it needs to go to in the topology of our network. And then there's the cluster actor, which is responsible for knowing like the state of the rest of the cluster. And that will then be able to read and write directly to other cluster nodes in our topology here. Also is responsible for checking to make sure the cluster is healthy, right? If we lose enough nodes, like we could be in some serious danger. So we need to know like where not to send messages and what to do if there's whether or not we need to like pause what we're doing while we wait for the cluster to recover. It's also like responsible for doing like the primary node data. It's like that's checking the messages that come in and being the leader for all the logs that we need to maintain in order to, preserve our messages. Here's a little bit of a visual diagram for what that looks like. You'll notice that there's a nice clean sequence for how a message might move through the system, right? Each of these individual components may have like data that's moving through them, but that data is being isolated, right? From they're not allowed to share that data between each other. If there's a piece of data that moves on, it moves on by itself. It is not retained. If you zoom into a little piece here, you can see a little bit more of the architecture, right? We have these different threads that are running, and they are, these queues are handling all the different events that may be coming in, pass through different parts of the system. We can manage this using like normal threading techniques, right? This is a very simple system. It's not like a generic framework that you can build actors off of. It's very specifically built for how BlazingMQ works, right? I like to recall back to this example we saw from earlier. I kind of skipped over this quickly, but there was this first assertion in here where we were checking some thread, right? This is part of that system. We're able to also use contracts here where we can check if the process that like where we are being called from is actually in the thread we expect, because this is part of the cluster's actor or the cluster actor. So again, we can actually check that like, these actors aren't being shared in between each other in particular. This works really well for us. It's a common pattern in a lot of distributed systems, especially our types of like message queues and stuff like that. So it's pretty nice, and it's nice that we can sort of apply it even at like, with the tools we have available to us. How much our time has?
25 minutes.
25 minutes. Okay, I still have a couple more things we could talk about here, but this is where I want to conclude our discussion on safety, right? So what did we learn?
It's a fun-sized problem.
It's a fun-sized problem? Fun-sized in what way?
Type 3 fun.
Type 3 fun, okay. That like a type theory joke?
No.
Okay.
There's the 3. It's like fun now and fun later. Not fun now, but fun later.
Not fun now, but fun
and
later.
not fun later. And yeah, you see the quadrant.
I see. Okay, well, so when we talk about what I think is right, when we talk about safety in C++, it's really important to qualify our definitions. There's a lot of research that I have done where someone's talking about safety and they're talking about a different type of safety than what like I'm trying to look for or what I think safety is. The breakdown of type memory and thread safety and all those other types of safeties is important when contextualizing a discussion like this, especially if you're trying to do like engineering work and like engineer for safety in your system. It's also important to know why you're engineering for safety in your system, right? Types, way more easily backported than language features here. So the more types that we have that are either more safe or have the ability for us to control when unsafety happens, or when preconditions, or what happens when preconditions are violated, specifically, is better for people like me and the systems that I work on. Whoa! Restart the computer now? No, thank you. Maybe we need to revisit some design patterns that we've talked, that we know about in software engineering, and reevaluate like exactly how much safety they bring to your code, and evaluate that as a feature of like how we engineer solutions and architect systems like this. And also that undefined behavior, maybe unfortunately, has utility, right? There's purpose to it, and we can't expunge it in the way that we can't expunge it from our language, and we don't necessarily want to. We can utilize it. I would like more controls over how it is when it triggers. So, does anyone have any questions? Or should I move on to a postscript about correctness? Good. All right. How much time do we have now still?
23 minutes.
23 minutes. Okay. I wasn't sure if I was going to be able to get to this, but it seems like I'm totally able to. Thank you. But also before we hit that slide, I'm going to talk about correctness here. Safety, correctness. What's the difference between the two? All right, we talked about safety being like when your program does something wrong. Yeah.
I always think of this as right. Safety is constraining what goes wrong, but it doesn't cause it to be correct.
Right.
And correctness is actually doing the right thing as opposed to just limiting the damage when something goes wrong.
Right. When correct, I can have safe code. I can have entirely safe code. I can in fact switch languages and go to a completely safe language and just be completely wrong, right? What that wrong means is is it logically doing the wrong thing? Sometimes I hear something referred to as logical safety, which I'm not sure has a difference from correctness, and I think that maybe conflates the two definitions. But you can't have a safe program and also be sure that it's correct, right? It's not necessarily doing the right thing, whether at a performance level or at a logical level or things like that.
So I think that that refers to stuff like the Toyota acceleration thing, right? Where they literally had a bug.
Mm-hmm.
It wasn't undefined behavior. They literally had a bug in the code, and it killed a bunch of people, right? That's not safe.
Oh, I see. Okay, so from the perspective of like a safety critical system, a logic bug, which would be I might think of as more of a correctness issue, ends up being like a safety, like engineering safety bug. Sure, absolutely, yes, that definition makes sense. Okay, right. How do we ensure correctness in code? Proofs. That's like a couple of slides from now, actually. But there's like I think I was expecting people to start with.
Define what you're trying to do.
Right. I need to define what I need to do. I need to have a certain expectation for how the code is going to do. How how do I assert that expectation?
Test.
Tests, yeah. That's like the most easiest thing, right? It's like we start with tests, right? All of our unit tests, integration tests. Sanitizers are, we talked a bit about sanitizers during the talk, definitely related to safety. And we end up using them more in like a testing scenario. So I do kind of group these in with tests, even though I think technically like they are just generally more about safety, right? But again, if you're unsafe, then you are not constraining the behaviors of your program in a way that, you know, can lead to incorrect behavior, right? All of these sanitizers are great. We do use all of them there. You should use them too where you can. Of course, we can't use them on every platform, but one platform is better than, you know, no platforms. We can also do proofs, system correctness verification. Sometimes we're working with a problem where we can actually literally mathematically describe it and prove it, right? One of the ways that we approach system correctness is through proofs, and I'll get to that in a second. There's also another way that we approach system correctness, and that's through like really strong system testing. There's this framework called Jepsen. There's a website made by a guy named Kyle Kingsbury. He's got this whole suite of frameworks that allow you to test specifically distributed systems. In fact, his website, I think, says something like improving safety in distributed systems or something like that. So I think that's the term he uses. And like we can like describe our cluster state and everything and use this a very robust system to like create nemesis processes, what he calls it, that will try to do harm to our cluster and check to make sure that when we claim a sort of abstract notion like our cluster will, you know, have at least or at most once message delivery, or at most once message delivery, which is what eventual and strong consistency means here. That we are actually like saying that for real, right? So this is just like checking that we are like delivering a message. Some message arrives. In a like, we can do things like, hey, in a distributed systems context, we can check that a random node, if it goes down, you know, we can still deliver our message. Interestingly, that's like fine with our eventual consistency model. But if you have a full network partition or there's like some sort of ring partition, then things start falling apart. But we're okay on our at most once or at least once delivery scenario. So that's good. We like that. We're being honest about the claims that we're making about our system. We also have proofs. TLA Plus is a proof or a theorem solving language. There's many out there. This is what we decided to go with. It's actually kind of interesting. From a distributed systems point, a lot of, if you remember that primary node that I was talking about before and how it has replicas, right? How do you select what that primary node is going to be for each of the queues that you are managing? This is a general problem called leader election. Leader election has like there's like well-known understood algorithms described through research that attempt to describe a fully correct behaving leader election algorithm, right? We can use a formal specification language in this case to actually take our idea of what our leader election algorithm should do and describe all the different states that our cluster can be in and all the different ways that it can transition through those different states, and then show that, you know, have this theorem solver go through and check every single state and make sure that we're not in any kind of we're not violating any kind of property that we want, like 2 leaders at the same time for a single queue. That would be really bad. We are directly, you know, inspired by the Raft algorithm. If you want to know more about that, there's papers and stuff. There's a really cool website actually that has like animations and stuff. It's pretty neat. You know, but we can actually like verify the correctness of our model, which in theory is like what our implementation is. Hopefully we didn't make any mistakes translating that. If you're curious what some of the TLA Plus code looks like, you know, here you go. Like, whoops, too fast, right? Here's all of our definitions and states, and then here's all the different ways our state can transition. It's kind of a neat thing to be able to work on a system where you can actually be like, okay, I can just fully describe and prove that my algorithm like is correct. And then I have to implement it in C++, but then it's, you know, we'll go on that later.
That's what was going to be my question. How do you know that this is actually describing what your C++ code is?
That's what I'm waiting for. Yeah.
Have you looked at kind of assisted theorem provers for languages, for programming languages, where you could actually annotate your code with these this kind of logic description, and it will both try to prove that the code matches that, and stitch it together to do the higher level correctness proof.
I am aware of that as an existing thing. I have not looked into that for our particular usage here. I have. Is that like a different theorem prover system? Is that like?
Yeah, it's not TLA plus. But
it's not TLA plus. Yeah.
It's analogous. And
Yeah.
there are a couple of different ones. Most of them are for C, but I think there are a couple that you can kind of make work with C++.
Yeah, I'm aware definitely of ways to try to, like a TLA plus, I believe there's a way to take this language and get like OCaml or Haskell out of it, which is cool, but like I can't use that. So I am aware of those that would like generate C, which is like,
so
I can use C.
Code, which are also really cool. Like and informal methods is usually called synthesis. But there are also ones where you can take code you write, but you just like describe how that code should plug into your theorem. And so it doesn't do synthesis at all, and lets you actually still control the code. And you can kind of like say like, well, I have to do a weird thing here for some kind of performance hack, right? Like I promise that this is what it means, though, to the theorem prover. And kind of narrow kind of the unproven thing without having to synthesize, like work with machine generated synthesized code.
Cool. I'd like to hear more about that. Cool. All right. So that's actually it now. Thank you. Here's links and stuff if you're curious more about Bloomberg. Any further questions? I know we covered, we had a lot of interaction, so I think maybe most people are. Okay, how much time we have left?
About 15 minutes.
Okay.
I guess I'm wondering why you think the only valid proofs are machine check proofs.
Oh, did I say that?
No, it's just you. I mean, it was kind of strongly implied because you said, well, you know, we verify correctness of code with tests, and I'm like, no, we don't, right?
We can help verify. I'm sorry.
We verify the proof in your head with tests. I mean, it's a CRC, it's not an actual proof, right? And then you can also machine verify parts of your proof that's in your head, and you can write that one down. And then you can connect the two, but you know what Chetler said. Like you can go, there's a spectrum, but in the beginning, there's a proof that's in your head about the correctness of the code.
Right, and then we write that down as a set of tests. But that's, of course, only as correct as we think it is in our head.
Yeah, like the tests are CRCs because you're only exploring certain traces through the program.
Right.
They're never like they're basically saying this trace did not hit any of the corner cases that I am trying to predict. That's all they're saying.
Right, and I imagine you're getting at like coverage as a way to like expand that, but probably not completely.
It's a good indication that you haven't forgotten an edge case, but it's also not foolproof.
No, tests are an incomplete tool for getting
CRC,
confidence.
They're very useful.
Yeah, they're useful, but they're not complete. The theme of this talk: useful but not complete. All right. Well, if there are no more questions.
Completely safe, you have to put your computer in a bunker because if cosmic rays can change a bit.
Yeah, the safest program is the one that's running on the machine that's turned off. Okay. Well, thank you, everyone.